Energy is tough to define, especially for a biology class. It's not really a concept, but it's something that you can't hold in your hands, so it makes it difficult. If you were to take a chemistry or a physics class, you might see some definitions like this, right? Energy is the capacity to do work. Energy it's held by an electron in motion around a nucleus. And for us, energy is trapped in and released from bonds. And you know that you release the energy from food and trap the energy in the bonds that you make growing your biological form. So work is the movement of an object as defined in a physics class, really. And we can kind of say that, well, we can say that the movement of an electron is what allows us as biological organisms to do work. All right, there's forms and types of energy. It gets all confusing. I know that you might be familiar with these two terms, and we're going to define them here. You probably might not see them again in this class, but let's use Sparkzilla here. Sparkzilla, you wind Sparkzilla, right? And there's a little button in the back of Sparkzilla, and you flick that button, and Sparkzilla lumbers forth and emits sparks. When you wind Sparkzilla, you're giving Sparkzilla potential energy. And when you flick that switch in the back of Sparkzilla, he takes that energy and converts it into movement or kinetic energy. When he does this, and he emits the sparks, a little bit of heat kind of comes off from the conversion of potential to kinetic. And yeah, little metal toys like this, they do heat up if you use them. These are the terms over here, forms of energy, that we may use again in this class. You will see your book talk about chemical energy. That's the energy trapped in the bonds of food. It's also the energy trapped in the bonds of you. I mean, you could be food for another animal, so it's all relative, isn't it? Your body will take that chemical energy and it will convert it into electrical energy. And you're saying to yourself, I'm not plugged into the wall. No, but every time you have a thought, some ions move throughout a neuron or a nerve, and that's what's pictured here, from your brain to a muscle, and that is electricity. So that's electrical energy. When that electrical energy gets to the muscle in your calf, as pictured here, it's not proportional to saying, that calf muscle will contract, and that contraction is mechanical energy. Every time energy here is converted from the apple to the nerve to the muscle, every time it's converted, a little bit of it is lost in the form of heat. And this is a truth, that every time you convert energy, a little bit is lost in the form of heat. Think about how a light bulb converts energy, electricity to light, and it also heats up. Think about your own body, how you convert energy of an apple to electrical and mechanical energy to power your muscles and brain, right? And you're 98.7. Or maybe you run higher, or maybe you run lower. It's an average. One of the things that you have to remember as a student in anatomy and physiology is that sometimes you have to go through basic vocabulary. I mean, some of these words that you see on the slide here, you might know them, right? And you might use them in certain ways, but here in this class, they take on a new meaning. So this is kind of like word association. This picture of Arnold Schwarzenegger here usually makes people think of steroids, thus called anabolic steroids, because the process named anabolism is a process that builds up molecules. Kind of like what I have circled down on the bottom left of this slide. A bunch of amino acids get strung into a protein. Another word we can use for that is synthesis. Your book likes to use that. So if your book uses these two terms, you know what they mean. If I use them in a quiz question or homework kind of question, you know what they mean. Over here on the right is the opposite. Catabolism is the process of breakdown or decomposition. And down here on the bottom, you have glycogen getting broken down into glucose molecules. And this is what happens when you get hangry. Your liver, because you're not eating, your liver will take some of its glycogen molecules and break them down into glucose. If you're diabetic, that might not happen. What is this picture on the right? Take a moment to look at it. It's kind of cute. It's the digestion or breakdown of a hamburger. Goes through the salivary glands, the stomach, the pancreas, gets divided up into the colon and the kidneys, liquid and solid. I like this title, Enzymes Make Things Happen. I like it because I like to remind you that the titles of our slides sometimes have really good statements. So a student put this on a test one time and I really couldn't disagree with it. That's right. But I would want you to use better vocabulary. So let's start simply. Anatomy. What are enzymes? They are proteins. And we know that proteins are folded to have a specific shape. So enzymes, what do? They're catalysts. What does that mean? I love using the example of Cupid. Cupid is a catalyst. Cupid shoots his arrow in the bow, shoots somebody in the butt, and then they end up falling in love, right? So Cupid makes something happen quicker than it would, and that's what a catalyst is. So all enzymes are catalysts. All enzymes can be used over and over and over again. Does that mean that the enzymes in your body right now are ones from birth? Probably not, but they do have a very long usage period. Enzymes are not multitaskers, and that's because they have a specific shape like proteins. If you're lactose intolerant, you know this because you don't make the lactase enzyme, could be a few reasons why. And the other enzymes in your body are not like, hey, I got this, no problem, I'll step up to the plate. Nobody's going to step up to the plate if you lose or don't have the ability to make an enzyme. All right, let's look at what enzymes do with a terrible schematic. Right, so let's define some words first. Let's take this one step at a time. Let's first define some vocabulary. Then let's talk about a concept. And then I want to apply it to this picture. And I'm going to redraw this picture very awkwardly. I think you might want to redraw the picture with me. So let's define some things. A substrate is what you start with. That's what you begin with that you want to change in this reaction with an enzyme. So the substrate is the beginning raw material. The product is what you end up with, right? Products are produced. So we've got raw materials and finished product. We also have something called an active site. And the active site, number one, it's on the enzyme. Look right now at the first picture on the left. And the big blue blob of the enzyme has the active site highlighted in purple. So the active site is a space on the enzyme, and it's the space where the substrate specifically fits into. Now you're looking at this picture, you're like, Amy, we have two substrates. Yes, you don't have to have one, you can actually have many. But the enzyme will have a specific place, a lock and key fit, where the substrate fits into the active site. Let's draw this. Here's our substrates, plural. What do you want this to be, glucose and fructose? Let's make it that, label them. Substrates, make one glucose and make one fructose. Draw me an enzyme. You have to draw it very specifically. You need a rounded part of the enzyme into which glucose can fit. You need a square into which fructose can fit. You got to have the shapes right. So this is our setup, right? And we know that the substrates and the enzyme are going to have to interact in some way. That's why they have a lock and key fit. So let's put them together. We've fit the substrates into the active site on the enzyme. That's a great statement that uses all of those, or most of, the vocabulary words, right? So we defined them, now we're using them. So what happens here is that the enzyme, in our example here, the enzyme is going to form a bond between the glucose and fructose, and it releases it as the product, and this product it's actually sucrose. Label that, sucrose. So let me ask you something. Is this an anabolic or a catabolic reaction? Anabolic, right? What if I flipped the slide and just turned it, you know what I mean, made mirror image? Then it would be a catabolic reaction. If you got to a question on a test quiz that asked you about this enzyme process, you had no idea what to say, you could use the term anabolic and catabolic. I give you a point. You could define substrate product active site. I would give you many points for that. But what I want you to be able to do is explain what happened in this picture and then apply an example like glucose and fructose making sucrose. One step at a time, one step at a time. I hate this slide, but I have to go over it with you. I have to go over it in every class. Enzymes lower something called the activation energy. And what this is the energy needed to start a reaction. Okay, so rubbing two sticks together is very difficult, right? That takes a lot of energy. Don't you wish you had a lighter? And that lighter would make it easier to start the reaction. So the difference between the sticks and the lighter are like the activation energy. Again, a hamburger will digest on the countertop. That's not quick enough. You need enzymes in your stomach to lower the energy that's needed to start those reactions of decomposition. So enzymes, they lower it, they don't contribute it. So it's like enzymes, think about if anybody was a track star that did hurdles, more to you, man, that's difficult. But an enzyme doesn't push you over the hurdle, it lowers the hurdle. It says, oh, you can't get over this? Let me lower it for you. It doesn't push you over it. It doesn't give you any energy to get over it. It just lowers it. I just want to point out sometimes that sometimes with enzymes, the reaction time may not increase. So it's not appropriate for you to say the reaction will go quicker. The point here is that the reaction will begin more quickly, right? Activation energy is the energy needed to start a reaction, right? So it kind of increases the likelihood that the reaction will happen. Hey, listen, your body will decompose when you die. If you put it out in a field or in the ground, it will decompose. But if you add fire, like we do in cremation, it will decompose a lot quicker. That's like an enzyme, right? Reaction more likely to happen. Let's do a graph. Draw this graph for me. We've got time on the bottom, so we're talking about proceeding in time, and we've got energy on the side. So we're going to talk about the rise and fall of energy. And let's draw a reaction, right? What happens is that there are conditions in the world, and there's a certain amount of energy, and if you want a reaction to start, you have to actually increase the energy. That's the activation energy, right there. That needs to be gained to get the reaction to start. So that's like all the energy that you would need to rub two sticks together to get a fire to start. It's a lot of energy. If I gave you a lighter, you wouldn't need so much energy, right? Look at how low the hill is here. The hill is the activation energy, and it's much lower here. So over in this picture on the right, look at the dotted line. That's a reaction without an enzyme. Look at the red line. That's a reaction with an enzyme. So the idea is, again, it's easier to start the reaction. The term denature means to change shape. And if enzymes have a very specific shape, yielding a very specific task that they do, then if you change that shape, they can't do their job, right? So enzymes, like, they rely on their specific shape to do their specific task. And if they don't have that shape, the active site changes and the substrate can't fit. What types of things can do this to enzymes? What can denature an enzyme or change its shape? Acids and heat. And that's discussed in another mini lecture. But also, some of these things that you have listed down here, painkillers and these high blood pressure pills on the right, these are enzymes inhibitors. In fact, you make an enzyme called the angiotensin converting enzyme, and what it does is it raises your blood pressure. So these drugs here, captopril and the other pril drugs, there are a certain class of drugs that lower blood pressure. On a personal note, I can't take these. I get a horrible cough. It just is what it is.